In this lesson on icing, we aim not only to understand the cause of aircraft and engine icing, but also the dangers it poses to aircraft operations. We'll also learn how to recognize and subsequently avoid icing conditions in the atmosphere. Firstly, let's examine why icing is so dangerous, in particular, airframe icing. What's the danger of airframe icing? An aircraft's wing has been carefully designed to create lift and reduce drag. Ice accumulation will significantly affect the shape of the aerofoil, and as a result, lift will be reduced. The greater the ice accumulation, the greater the loss of lift. Ice can also disrupt the flow of air over the airframe, causing extra drag. Another performance factor to consider is weight. Significant ice accretion can increase the weight of the aircraft. To oppose this extra weight, we need to increase lift. And as we've just stated, ice on the airframe will have the effect of reducing lift. The combination of these effects increases the stall speed of an aircraft and reduces its stability. In flight, this spells danger. Icing also has adverse effects on aircraft instruments. It can block vents and ports, and so, in icing conditions, be wary of instruments which rely on these vents and ports for accurate readings. Aircraft icing occurs because of the presence of supercooled water droplets inside clouds. These exist as large or small droplets, or both, depending on the outside air temperature and the type of cloud in which they are found. Supercooled water droplets are water droplets which are still in a liquid state, even though the temperature is below 0 degrees Celsius. This situation prevails only when there is nothing for the droplets to freeze onto, that is, when there are no freezing nuclei. Supercooled water droplets can exist in the atmosphere at temperatures as low as minus 40 degrees Celsius. As you can imagine, there is one surface which, when presented to the supercooled water droplets, will cause them to freeze. This is, of course, an aircraft. As you can imagine, there is one surface which, when presented to the supercooled water droplets, will cause them to freeze. This is, of course, an aircraft. The type of airframe icing depends on the size of the droplets present within the cloud. Let's examine the small supercooled water droplets first. These can be found at temperatures between minus 15 degrees Celsius to minus 40 degrees Celsius. Since they are so small, the moment they come into contact with the leading edges of an aircraft, they will freeze instantly. As the diagram shows, over time the ice will accumulate on the leading surfaces of the aircraft. This type of icing is known as rime ice. It's characterized not only by the way it builds just on the tip of the leading edges, but also by its color and texture. It's opaque or milky in appearance. This is because air is trapped inside the ice because the freezing process occurs so rapidly. It also has a rough sandpaper-like texture. This is because small droplets freeze straight away and accumulate to give a granular growth. It looks and feels very much like the ice that grows on the inside of domestic freezers. The large supercooled water droplets are found at temperatures between 0 degrees Celsius and minus 15 degrees Celsius, and they freeze in a very different way. Because of their size, they don't freeze straight away. When the droplet first strikes the leading edges of the aircraft, only that part touching the aircraft will freeze instantaneously. The remainder of the droplet can then flow backwards, slowly freezing as it comes into contact with the skin surface. This buildup is characteristic of this type of icing called clear or glazed ice. Clear ice looks like glass and is mostly transparent, making it difficult to spot. It's clear because there is no air trapped inside. The freezing process is slow enough to allow the air to escape. This icing is very dangerous. It can rapidly accumulate on the wings and is more difficult to remove. On most occasions, though, it's unlikely that you will experience just one type of icing. It's far more likely you'll experience both forms. This type of icing is called mixed ice and incorporates both rime and clear ice characteristics. There's a third type of icing called rain ice or freezing rain. This type of icing is the most hazardous to aircraft operations. In order for it to form, warm air must overlie very cold air, which is below 0 degrees. This is only possible on a warm front, like the one shown here, or an occluded front. The cloud and rain is being produced inside the warm air as it rises up and along the front. But notice that at this point, the rain is falling into air below 0 degrees, and it may become supercooled. If an aircraft were to be flying in this area, the rate of accumulation of ice is so severe that within a very short time, the aircraft will not be able to sustain flight, making diversion a necessity. Be cautious when flying through warm fronts or occlusions, especially if the air ahead of the front is very cold. If you start to encounter freezing rain, turn away and leave the area immediately. There is one more type of icing. This is called hoarfrost, and it's the only icing that can develop clear of cloud. This icing is identical to that which can develop on car windscreens on frosty nights. It can develop on an aircraft in flight or on the ground. On the ground on clear nights, when the surface temperature falls below 0, water vapour can turn directly to ice, and hoarfrost can be seen on the surface as the ice crystals are created. It's important that prior to flight this ice be removed, since it can interfere with the airflow over the aircraft. This kind of icing can occur in flight in clear air when an aircraft rapidly climbs through an inversion. If the initial air temperature is below 0, then the skin of the aircraft will also be below 0 degrees. But when it climbs and enters the warmer air, the air travelling over the skin is cooled, and sublimation can occur, creating ice crystals and frost. This can also be observed in a rapid descent from high altitude where the aircraft's skin temperature is still below 0. As the lower, warmer air flows over the skin, it again can be cooled to freezing point. If your windshield is suffering from this icing, then the danger is that you will not be able to maintain visual reference with the ground. We mentioned earlier that both the outside air temperature and the cloud type determine the size of the supercooled water droplets. Cumuliform type clouds frequently have strong vertical updrafts of air moving within them. They can therefore support significant numbers of large, supercooled water droplets. As a result, a pilot can expect moderate or even severe clear ice within these clouds, especially in flight to just above the 0 degrees Celsius level. In cumulonimbus clouds, the updrafts are even greater, and so the icing risk is always severe. Avoid these clouds, not just because of the icing risk, but because of the other dangers posed by them. In layered cloud, the icing risk is usually much lower because of the lack of vertical air development. Even if the temperatures were suitable for the formation of large supercooled water droplets, the cloud has little capability to support them, and even less capability of supporting large quantities of them. As a result, we can generally expect only small droplets, and therefore only light rime ice. The cloud which is an exception to this is nimbostratus. It can have the upcurrents to support the large droplets, making the icing risk moderate or even severe. Having considered the danger of airframe icing, let's now consider another type of icing that you may experience. This is called induction icing. Shown here is a simple induction system. The first of this type of ice is called impact ice. This occurs as snow or supercooled water droplets sticking or freezing instantaneously when they come into contact with the walls of the intake chamber and air filter. It can eventually block the air intake completely, causing the engine to stop. Any type of piston engine can suffer from this type of ice buildup. Fuel-injected aircraft have an alternate air supply to feed the engine when the normal air intakes are blocked. When the relative humidity is higher than 50% and the temperature lies between about -10 degrees Celsius to +30 degrees Celsius, another type of ice, called carburetor ice, can build up within the induction system. This can be caused in two ways. As air passes through the venturi, shown here, static pressure decreases and the temperature of the air will fall, possibly causing ice to form within the venturi. The throttle butterfly valve has a similar effect. On low power settings, the butterfly valve is almost closed and restricts the airflow. This acts like the venturi, and a drop in temperature can occur, causing ice to build up and possibly jam the throttle. The effect of the vaporization or evaporation of fuel as it leaves the fuel jet, shown here, may combine with this to aggravate the situation. This process causes latent heat to be absorbed and thereby reduces the temperature, possibly leading to ice formation. The combined effect of these icing processes will cause a piston engine to be starved of air, causing it to run rough and possibly stop. However, there is a way to combat this potentially dangerous situation. By selecting carb heat, we can divert warm air from around the engine compartment into the induction system to help melt the ice and prevent starvation of the engine. However, as hot air passes through the engine, performance will initially deteriorate further because of its reduced density. This may appear rather alarming, but don't worry. This is a sign that the hot air is doing its job. Similarly, ice and liquid water which may pass through the engine may again cause it to run rough. But as before, this is a sign that it's working. After a few moments, the engine will start to operate normally again. This completes the lesson on icing. We've dealt with some very important issues that a pilot must be aware of. Icing is dangerous. Being an informed and educated pilot is the best way to counter that danger. Above all, expect airframe icing in cloud whenever flying above the freezing level. At the private pilot level, you should stay well clear of any cloud, especially convective clouds. Lastly, when on low power setting in the descent, for instance, especially when the humidity is high, always be prepared for a rough-running engine caused by carb icing. Remember that the application of carb heat may momentarily cause the situation to worsen. Keep the carb heat applied and the engine performance will improve.
We may define an air mass as a large